Hello. In this video, we're going to continue our study of infinite sequences and series. And more specifically, we're going to use some observations about these examples I have stated on the first page here. We're going to use some observations about these to make a statement of general fact about the terms being added in an infinite series and whether that tells us anything about whether the series diverges or converges. And then we're going to use that general fact that we'll state and apply it to some examples. And then I'll show you a really interesting, famous example of an infinite series that we're going to see pop up a lot for the rest of the semester. So let's look at these examples in turn here. Why do they each diverge? Well, think of this first example as saying 1 plus 2 plus 3 plus 4, and, well, I hope I don't have to say too much here to convince you that this is a divergent series in the sense that it doesn't add up to a specific finite value. So try to have that notion of a series converging, meaning it adds up to the total of all of the terms is some specific finite number. So a divergent just means it doesn't do that. So in this first example, if I do 1 plus 2, I get a total of 3. And then if I do 1 plus 2 plus 3, I get a total of 6. And then I get a total of 10 and 15. And as I keep adding more terms, the running totals, the partial sums, grow and grow and grow to positive infinity. They're just going to get bigger and bigger and bigger. In the second example, I have the same situation happening where the partial sums are growing, but they're just doing so a little bit more slowly than the previous example. If I add up the first one term, I get 1. If I add up the first 2 terms, I get a total of 2. If I add up the first 3 terms, I get a total of 3, and so on and so on. That's also diverging away to positive infinity. Now, the third example down here is a little different because it's not quite as obvious maybe what's happening with the terms themselves that are being added together in this series. So do you notice anything about a pattern in the terms? I see the numerators are all 1, 2, 3, 4, 5, so the whole numbers. That's coming out of the n in the formula there. And the denominators are all, well, let's think of that as 1 over 1. So 1, 3, 5, 7, 9, 11. Those are all the odds. And that's precisely what the 2n minus 1 in the denominator does. When n is 1, 2 times 1 minus 1, there's the denominator of 1. When n is 2, I get a denominator of 3. And when n is 3, I get a denominator of 5, and so on, and so on, and so on. So another way to say what we're about to observe about this is not just a pattern in the numbers that are happening in these terms, but do you notice anything about what happens to them as I go further and further to the right, as I go down the series? Or in other words, what if I take a limit as n goes to infinity of that expression, that formula? So even just forget everything we know about series for a second. We'll come back to that momentarily. But just think about this sequence, n over 2n minus 1. As n gets bigger and bigger, n goes to infinity and 2n goes to infinity. But in the limit, their ratio is going to approach 1/2. You could, let's see, divide top and bottom by n here and see that this part's going to go to 0. Or you can do L'Hopital's rule once, or just kind of look at a graph, whatever you can do to convince yourself that this limit is correct. I hope you can see that. So essentially what that means in terms of our series is that way down the line, if I go dot, 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 dot for a really long time and I go down to like the millionth term, I have pretty much effectively, not exactly, but I'll say like roughly way down the line in the series, I have something pretty close to 1/2, plus the next term, pretty close to 1/2, plus the next term, pretty close to well, way down the line, this series is almost exactly like adding 1/2s forever and ever and ever. And if adding 1s forever and ever and ever made the sum approach positive infinity, this is going to do that too. If I just keep adding 1/2 and 1/2 and 1/2 and 1/2 forever, the sum is going to diverge to positive infinity. And so the commonality between these three examples is that in the first one, the terms being added themselves are growing. So of course, as I add them together, the totals, the partial sums, the running totals are going to grow to infinity. In the second example, the terms are constantly 1. They're the fixed number. So although it does more slowly, of course, they are also going to grow in running totals to positive infinity. And in the third example, the numbers are not constant. They're decreasing. If I look at 1 and then 2/3 and 3/5 and whatever, these are all decreasing down to 1/2. But what's important is that that number is not 0, because that means my terms are decreasing down to something that I'll just add to itself over and over and over, and that's going to make the running totals diverge up to infinity as well. And so here's the thing that we can conclude from the observations we made in those examples. If I have an infinite series and the terms being added themselves, the terms in the sum that I'm in the series that I'm adding together, if those terms don't go to 0, if they don't get smaller and smaller and approach 0, then there ain't no hope for this series to converge, to add up to a specific finite number. Because essentially it will amount to something like this, where I'm adding numbers that are getting bigger, or I'm adding the same number over and over and over, or I'm doing something almost like that in the long run, where the numbers are changing, but they're becoming more like a situation where I'm adding the same number itself over and over and over. Something like that is going to happen if the terms being added themselves don't go to 0. So in other words, if they if the terms don't go to 0, then the series diverges. That's what I have stated in the first bullet point here. So I'm hoping that from those first 3 examples on the first slide, you can convince yourself that this way that it's stated right here, that's a true statement. That's what I have outlined in the first bullet point. But why am I saying something about this second bullet point? This is so important because I've seen this same mistake happen over the years. There's a tendency, an inclination, a temptation, I could say, and I understand it a little bit, but there's a temptation to turn the logic around and say, well, that must mean that if the terms that I'm adding do go to 0, then the series must converge for sure. And that's just not the case. That is just not true. And I'm going to try to use the rest of this video, or most of it, to convince you of that and try to nip that temptation in the bud. And I hope in the process I'm not putting bad ideas in your head you didn't already have. But essentially, if the terms an that I'm adding together in the series, if those terms do go to 0, that just means we have something to do. It just means we've got a neat question. We have an interesting series. We have more to investigate. If the terms are going to 0, that means there's hope. It might converge, but it might not. And we have to explore more to be sure. When the terms do go to 0. So I'm going to come back very soon and give you, in fact, hopefully a striking example that you can have in mind to remember how important this logic is. I'm going to give you pretty soon an example of a sequence whose terms go to 0, but in such a way that when I add the terms of those sequence and I look at the series, it will actually diverge, believe it or not. And so hopefully that will be something you can have in mind as this thing is possible. It is possible to have the numbers that I'm adding shrink away to 0, but still cumulatively they add up to a big infinite total. But I'm going to come back to that in a minute. Let me just talk about the logic about why this is a temptation, but also why it's just a might on when I turn the logic around. So that divergence test theorem we just saw is a conditional statement. It's something of the form, if blah-blah blah blah, then blah 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 blah. So we usually call the if part the hypotheses, the assumptions of the statement, and then the then part the conclusion of the statement. So if I start from a conditional statement like that, if P then Q, it's very common to just use letters to replace the collection of hypotheses and the conclusion. Then if I turn that logic around, and I say if Q then P. So in other words, if I flip-flop the P and the Q in the statement, then I get another conditional statement, another if yada yada then blah blah blah, and it's known as the converse of the original statement. The converse means flipping the order of P and Q. So if I do that, then if the original statement was true, if P then Q, if that's a true statement, then it turns out the converse statement might be true or it might be false, and it depends on what the original P and the Q are. So I'm going to give you some examples of how it can go both ways. Consider this statement down here. If a whole number is a multiple of 6, then it must be even. I hope you can convince yourself that this is a true statement. 6, 12, 18, 24, all the multiples of 6, they're all even. Because to be a multiple of 6, you got to be a multiple of 2 and 3, because that's what 6 is, 2 times 3. So this is a true statement. However, the converse, reversing the order, if I take the must be even part and I put that in the beginning, so there's Q. If I take the multiple of 6 part and I put that at the end, that's P. And I look at this whole statement down here, that's a false statement. If a whole number is even, then it must be a multiple of 6. Because, like for example, 4 is not a multiple of 6, but it's even. And that's a way to show you that that statement's false. So there's an example where a true statement, if I flip-flop the order of the if and the then parts, the Q and the P, then it becomes a not true statement. That's what I meant by the converse might be false. There's an example for you right there. However, sometimes if I flip-flop that order, it might still be a true statement, and that's what we're about to see in the second example down here. If I have two odd whole numbers, then their product is odd. That's what this is. If whole numbers A and B are odd, then their product is odd. Well, I can turn that logic right around, and it turns out to still be true. If I have a product of whole numbers, and the product is odd, then the individual numbers themselves must be odd. That's a true statement. Play around with some examples for yourself. 3 times 7 is 21. Those are both odds and the product is odd. But vice versa. Let's say I told you that I have a number in mind, 105, let's say, for example. And it came from a product of whole numbers. Well, that could be 5 times 21. It could be 7 times 35. It could be... Hey, why the hey not? It could be 105 times 1. Those are all odd times odd. And so the turned around, the converse version of this statement is also true. And so I could actually say down here, combining those two statements together, a product is odd of whole numbers if and only if. And that phrase here is saying that it's both of those logic pieces. I can turn them around and combine them together. A product is odd if and only if both of the factors are odd. And that's a different situation than what we had up here with the multiples of 6 and even. And so hopefully all of this is more evidence to remind you that just because this statement up in the theorem box is true does not mean I can turn the logic around and assume that the converse will be true. Because sometimes it is, and sometimes it is not. Okay, next, let me give you that example of what I promised. Sorry, let me back up a second to remind you what I'm going to do. This divergence test theorem says if the terms being added in a series do not go to 0, then the series must diverge. It has no hope to converge. And so I said it's possible for the terms an being added to go to 0, and yet the series still diverges. That's what I'm going to show you right now. An example of a series where the terms approach 0, but the series diverges. So this is a very famous example called the Harmonic Series. So first of all, the sequence of terms, the harmonic sequence, is 1, a half, a third, just 1 over the whole numbers. And it's called harmonic because it has something related to the frequencies and pitches of notes and the intervals between notes and things like that. I gotta be honest, I don't know a whole lot about that myself, but I know it's related enough that that's why we use the term harmonic, which also comes from music. I do frankly wish I knew more about the connection, and I'll read up on that more. But for the moment, I'll just tell you that there's a connection there, whatever it is. And so I hope you can see that that sequence is converging to 0. The limit of those terms is 0. Because I have 1 over larger and larger and larger denominators. And yet, what do I mean by the series diverges to infinity? That's what I'm getting at in this table over here. the partial sums grow forever to positive infinity. Now, what do I mean by that? In this table here, I have a column for n. That means the index, the number of terms that we're adding together. N is the number of terms being added together. And S sub n is the nth partial sum. It's the running total of what I would get if I added up the first n terms. So for example, if I add the first 1 term, I get a total of 1. If I add the first 10 terms, if I added up the first 10 terms of the series, which by the way, you could do quite laboriously by hand on a calculator, or use some technological tool like here I'm showing you how to type the syntax into Wolfram Alpha. I can say sum 1 over n, and then just give the limits from n equals 1 to n equals 10, and it will add that up for me. And I can see I get a nice fraction, 7,003, blah, blah, blah. Or it rounds it to a decimal here, 2.9289. And that's what I've rounded off here in my table to say 2.92. That's that number. Then I could go back there and change the upper limit from 10 to 100. So let's write that as 10. I can never find the caret. Where? There it is. Squared, or 100. And say go, that's going to, whoa, there's a big fraction. But down here I see 5.187. That's the running total that I have here after adding 100 terms from this series. The total is 5 something. If I add 1,000 terms of this series, the running total is 7 something. And if I add 10,000 terms, the running total is 9 something. And these are growing pretty darn slowly, but they are growing. And not only that, I want to point out that they're growing in a consistent manner. Look at the difference between, for example, 2.9 to 5.1. That's a difference of approximately 2.2. I'm really rounding off here, but it'll make my point close enough. 5.18, let's call it 5.2, and 7. I know this isn't how we usually round, we call it 7.4. That difference is about 2.2 as well. And then 7.5 or so to 9.7, that's a difference of 2.2 again. That's a difference of about 2. Like every time I multiply by 10 going down here, I end up adding about 2.2 in the running total. And so there's something interesting happening there in that these running totals, these partial sums, they're growing logarithmically. As the input multiplies by 10, the output adds by a specific number. And just to speed up the process slightly down at the bottom here, I went from 10 to the 6th or a million down to 10 to the 9th, which is a billion. And then 10 to the 12th, which is a trillion. And those are jumping up by about 7. You see how the difference is about the same, well, approximately 7 each time, as I'm multiplying by 1,000 each time. This shows you the logarithmic growth of the partial sums. So if I do n here, and I plot s sub n on the top, it's growing very slowly, but it is going to go up to infinity. The logarithmic function increases really slowly, but it does rise forever. And so in that sense, this series, I hope this is evidence, maybe not a proof yet, but this is evidence that the series diverges. The running totals, the partial sums, just get bigger and bigger and bigger, really, really slowly, but they do grow forever. If you want to make your series add up to something a little more than 12, you just got to take 100,000 terms. If you want to make it add up to a little bit more than 21, you got to make the number of terms a billion or more. If you want to make the total add up to, let's say, 100, well, gosh, I don't even want to think about how big a number you need, but you can get there if you wait long enough. Now, let me be a little more specific and show you using some crafty algebra why this series diverges by showing you that the running totals, the partial sums, are bigger than essentially adding up 1/2 forever and ever and ever and ever, which we already saw way back on page 1, that adding a number to itself over and over will cause the series to diverge. The running total just gets bigger and bigger. So here I've written out some of the first few terms of the harmonic series. I've also written it in summation notation to help remind you that we need to convert from one to the other. I'm developing our fluency and going back and forth. And now in the second line, I've just grouped off some of the terms. I've separated out the 1/3 and the 1/4, and then the next 4 terms for reasons that are about to be seen here. So I'm going to take this sum so far, and I'm going to replace some of the terms. I'm going to keep the 1 and the 1/2, and I'm going to make the 1/3 into a 1/4, and I'm going to keep the 1/4 alone. And then in the next block of 4 terms, I'm going to make all of them 1/8 plus ... Now, what have I really done? I am not legally allowed to write equals here because I changed some crap. I can't say that. So what could I legally say? Well, the 1 became a 1, so I didn't change anything. The 1/2 became a 1/2, I didn't change anything. But look at the changes. When I made the 1/3 into a 1/4, it got smaller. 1/4 has a bigger denominator than 1/3, so it's a smaller value. And 1/4 to 1/4, that didn't change. So it feels like maybe I'd be allowed to write greater than here because the total so far over here is smaller than the total of those. I made all of the terms the same except one of them got a little smaller. How about the next block of 4? A 5th to an 8th, that also got smaller. 5 is a smaller number than 8. This is a bigger denominator, so it's a smaller fraction. And same thing with the 6th and the 7th. And then I kept the 1/8 alone, so I don't really need to point that out. But in this next row, each term in the sum is either the same as it was above, or it's a smaller number, and that's why I'm allowed to legally write this greater than. I am confident that the sum of all of the crap up here is something bigger than the sum of all of the junk down there, based on what I did. Okay, so now let's see what I've accomplished by doing that. I'm going to write equals again because I'm not changing anything. I'm just going to notice what I've accomplished. Here, the 1, that's still a 1. The 1/2, that's still a 1/2. And look at this. I have 2 things that add up to, I have 2 1/4ths. So they add up to 2/4ths, or hey, 1/2. Over here, I have 8ths. How many of them? I got 4 of them. So I have 4/8ths. Hey, look at that. That's also 1/2. That's weird. Now imagine I did this for the next block of 8 terms. The ending term was going to be 1/16 plus a bunch of stuff. So if I made all of the next terms, a 9th, a 10th, 11th, all the way down to 1/16, if I replaced all of those with 16ths, I would have had 8 of them, and I'd have 8/16. And look at that. Those are all 1/2s. That's why I blocked them into groups of 2, and then 4, and then 8, and then so on. And weren't we just talking on the first slide about how adding 1/2 to itself over and over and over and over is just going to make the running total, the partial sums, grow and grow to infinity? That means this series down here is already divergent. It already adds up to an infinite running total. And didn't we notice that this harmonic series I started with up here is bigger than the one at the bottom? So if this stuff down here already adds up to infinity, and this thing up here adds up to something bigger, doesn't this also add up to infinity? It has to. That's the proof, the verification that this series really adds up cumulatively in total to a huge number, just grows and grows and grows. And that's what we were seeing with this spreadsheet, this table over here on the left. The running totals get bigger and bigger. This over here was a way to turn that observation into something a little more tangible and concrete that I can observe and say, oh yeah, it's kind of like, and in fact bigger than, adding 1/2s forever and ever and ever. Now I have to make clear, this is something that I would like you to follow along with this logic, and maybe not even just the first time talking through this. Take the video back a little bit and watch this part again. Maybe 2 or 3 times it'll start to click a little bit. I'm hoping you'll be able to follow this logic. I don't want you to be able to come up with, to invent this method. This is something that I want you to just follow along. But I really want you to focus on the conclusion of this, which is the divergence test says if the terms of a series go to 0, that means we have something interesting to do. If the terms of the series do not go to 0, I can say the series diverges and move on.